Gravitational force. This was defined by Newton, identified by Newton, and the statement of Newton goes like this. Every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and is inversely proportional to the square of the distance between them, and this force acts along the line joining the two particles. Every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses and is inversely proportional to the square of the distance between them, and this force acts along the line joining the two particles. This is how we state the gravitational force, gravitational law. Now, mathematically, if m1 and m2 are two masses present at a distance d, the distance between the centers of the two masses is say d, the force acts on both the particles shown in the figure. On m1 it is to the right, on m2 it is to the left. It is the same force, and we notice that this force is directly proportional to m1 m2 and inversely proportional to 1 by d square. So combining these two, we use a gravitational constant capital G and write the relation for force, and write the relation for force as F is equal to G m1 m2 divided by d square. Capital G m1 m2 divided by d square. This relation we have already come across in high school level. So the gravitational force is given by the relation F is equal to G m1 m2 divided by d square. Nature of gravitational force. Nature of gravitational force. It is an attractive force. It is an attractive force. It is an action-reaction pair. It acts on both the bodies. It is an action-reaction pair. It acts along the line joining the centers of the two masses. It acts along the line joining the centers of the two masses. The force between two masses is independent of the presence of other masses. So it is independent of the presence of other masses. It is the weakest of all forces. It is the weakest force in nature, and it is a conservative force. It doesn't depend on the path followed by the particle. It is a conservative force. It depends only on the positions but not on the path. Gravitational force, it applies everywhere and between any two particles. Wherever may be the particles and whatever may be the distance, this force is present everywhere between any two particles. It is believed to be communicated by massless particles called gravitons. We imagine that it arises due to the exchange of a particle known as graviton. It results due to the distortion of space-time. It results due to the distortion of space-time. Universal gravitational constant capital G. The relation for gravitational force F is equal to capital G m1 m2 by d square. Here the constant capital G is known as universal gravitational constant. Its value is 6.67 into 10 to the power of minus 11. Its value is 6.67 into 10 to the power of minus 11. Units are Newton into meter square per kg square. Newton meter square per kg square. The same constant can be used between any two masses wherever they are situated. So it can be used between two particles like nucleons as well as two massive particles like Earth and Sun, and we can use this formula, this relation, wherever the particles are situated. Whether there is a medium between the particles or not, we can use this relation. We can use this relation. We can use this constant. Hence, it is called universal gravitational constant. Relation for acceleration due to gravity small g. Let us derive a relation for acceleration due to gravity small g. In the figure, capital M represents the mass of the earth, the big circle represents the earth, and the mass of the earth is capital M and radius is capital R. The small circle represents a particle of mass small m, which is at a height h over the surface of the earth. Let us take capital R plus small h is equal to small r, that is the separation between the two masses, centers of the two masses. So the distance between the small m and capital M is taken as small r. And let us use the relation given by Newton. F is equal to capital G m1 m2 by d square. In this relation, let us take m1 is equal to capital M and m2 is equal to small m. Then distance d is equal to r. Then the relation for the force between the two masses, earth and the small body of mass small m, is given by capital F is equal to capital G capital M small m divided by small r square. Capital G capital M into small m divided by capital R square. This force is given as the gravitational force on a body of mass m, where G is acceleration due to gravity small g. So F is equal to m into small m into small g. This is gravitational force. The force of attraction is manifested as the gravitational force mg. Hence, small m small g is equal to, small m small g is equal to capital G capital M into small m, capital G capital M into small m divided by small r square, Small m gets cancelled. Hence, we get the relation small g is equal to capital G capital M by small r square. Small g is equal to capital G capital M by small r square. This is the relation for acceleration due to gravity. Acceleration due to gravity. Acceleration due to gravity depends on 1. The mass of the planet Earth and the distance of the point from the center of the Earth. The distance of the point from the center of the Earth. It depends on mass of the Earth and the distance of the point from the center of the Earth. Variation of G. Variation of acceleration due to gravity. Near the surface of the Earth, acceleration due to gravity G is given by capital G capital M by capital R square. Instead of small r, we take the radius of the Earth. So, on the surface of the Earth, the acceleration due to gravity small g is given by capital G capital M by capital R square. The radius of the Earth is not constant. It is more at the equator and less at the poles. Hence, acceleration due to gravity varies with the radius of the Earth. Wherever the radius is small, less, the acceleration due to gravity is more. The acceleration due to gravity is less where the radius of the Earth is more, that is at the equator. And the acceleration due to gravity varies with altitude, that is with the height. As we go up into the above the ground, then the acceleration due to gravity decreases. It can be estimated with the relation gh is equal to gm by r plus h whole square. The acceleration due to gravity varies with depth. As we go into the Earth, the acceleration due to gravity varies because the effective mass which creates acceleration due to gravity will decrease as we go into the Earth. And it also varies with the mineral deposits. Wherever the mineral deposits are present, the density is more, hence acceleration due to gravity increases. A relation for variation of g with height with altitude. Near the surface of the Earth, the acceleration due to gravity g is given by gm by r square, capital G capital M by capital R square, small g is equal to. At a height h, gh is given by small g, h is given by capital G capital M divided by r plus h whole square, capital R plus h whole square. We can write from the above relation, from the relation small g is equal to capital G capital M by r square, capital G capital M can be written as small g r square, where small g represents the acceleration due to gravity near the surface of the Earth. So we are writing the acceleration due to gravity at a height small h in terms of acceleration due to gravity on the surface of the Earth. This relation is gh is equal to gr square by r plus h whole square. This can be rearranged as gh is equal to small g whole divided by 1 plus h by r whole square. Gh is equal to small g by 1 plus h by r whole square. Variation with height. The relation is gh is equal to g by 1 plus h by r whole square. This relation is used whenever the h height is comparable to the radius of the Earth. The radius of the earth is about 6,400 kilometers. So whenever we take h as 2 kilometers, 4 kilometers, or some about 32,000 kilometers, like this, when the height is comparable to the radius, we consider this relation. But when the height is very, very small, about 1 or 2 kilometers, when the height is comparable to radius, means about half of the radius, 1/4 of the radius, 1/3 of the radius, like this, or double the radius, we can use the above relation GH is equal to G by 1 plus H by R whole square. But for small distances like 1 kilometer, 2 kilometers, etc., we can modify this relation and find the approximate value of acceleration due to gravity. For this purpose, we write the equation GH is equal to G into 1 plus H by R whole to the power of minus 2. G into 1 plus H by R whole to the power of minus 2. If H by R is very, very small, by using expansion of the series, this can be written as small g into 1 plus small g into 1 plus minus 2 into H by R. This can be written from the expansion of the series. We get such an expansion of the series in mathematics. Using the mathematical expansion result, we can use the value of GH as approximately equal to, not exactly equal to, G into 1 plus minus 2 into H by R. So, the approximate relation for finding acceleration due to gravity for small heights is given by GH is equal to G into 1 minus 2 H by R. Small g into 1 minus 2 H by R. Variation of G with depth. Variation of small g with depth. Near the surface of the earth, the acceleration due to gravity G is equal to Gm by R square. Near the surface of the earth, small g is equal to capital G capital M by capital R square. Let us write this relation in terms of density of the material of the earth. In terms of density of the material of the earth. Earth can be considered as a spherical body. So since its radius is R, the volume of earth is 4 by 3 pi R cube. 4 by 3 pi R cube. If we assume that the density of the earth is uniform and represent with rho, if we represent the density of the material of the earth as rho, and if we assume earth is composed of uniform density, then the mass of the earth can be written as 4 by 3 pi R cube rho. 4 by 3 pi R cube rho. By substituting this value in the relation G is equal to Gm by R square, we get small g is equal to capital G by R square into 4 by 3 pi R cube rho. Capital R square gets cancelled, and we get the relation for small g as 4 by 3 pi capital G capital R rho. This is the relation for acceleration due to gravity in terms of the density of the material of the earth. So in terms of the density of the material of the earth, we can write the acceleration due to gravity, the relation for acceleration due to gravity as small g is equal to pi capital G capital R rho. This is when the radius of the earth is considered as capital R. At a depth d, the radius of the sphere that creates acceleration due to gravity is r minus d. At a depth d, the radius of the earth that creates acceleration due to gravity is only r minus d. Hence, the acceleration due to gravity relation becomes Gd is equal to, d represents depth, 4 by 3 pi g into r minus d into rho. 4 by 3 pi g into r minus d into rho. Like this, using this relation, we can calculate acceleration due to gravity at a depth d. Variation of g with depth. Near the surface of the earth, the acceleration due to gravity small g is equal to capital G capital M by R square. At a depth d, the relation is derived to be 4 by 3 pi g into r minus d into rho. Gd is equal to 4 by 3 pi g into r minus d into rho. Near the surface of the earth, in terms of density, g is equal to 4 by 3 pi gr rho. 4 by 3 pi gr rho. So the ratio Gd by G is equal to r minus d by r. The ratio Gd by G is equal to r minus d by r. This relation gives the value of GD, acceleration due to gravity at a depth d, in terms of acceleration due to gravity on the surface of the earth. Acceleration due to gravity at a depth d in terms of acceleration due to gravity on the surface of the earth. So GD by G is equal to R minus D by R. Study of variation of G both with height and depth. Let us take the relation for the acceleration due to gravity near the surface of the earth. Small g is equal to gm by r square. At a height h, gh is equal to gm by r plus h whole square. At a depth d, it is gd is equal to, in terms of acceleration due to gravity on the surface of the earth, is gd by g is equal to r minus d by r. Let us take the distance from the center of the earth as small r. Let us consider the distance from the center of the earth as small r. Then small r becomes equal to capital R plus h when the particle is above the surface of the earth, and when it is inside the earth, then the distance becomes capital R minus d is equal to small r. The distance from the center of the earth can be represented by small r, and the small r is equal to capital R plus h for outside the surface of the earth, and for inside it is r minus d. Then gh is proportional to gm by r square. Gh is equal to gm by r square, and gd is equal to g by capital R into small r. G by capital R into small r. Let us take these two relations for the study of variation of acceleration due to gravity both with height and depth. For the study of variation of acceleration due to gravity, we use the relation g is equal to gm by r square near the surface of the earth. At a height h, gh is equal to gm by r square, or gh is proportional to 1 by r square. At a height h, gh is proportional to 1 by r square. At a depth d, gd is equal to g by capital R into small r. G by capital R into small r, or gd is proportional to r. Since small g and capital R are constants, gd is proportional to r. So gh is proportional to 1 by r square and gd is proportional to r. So outside the surface of the earth, acceleration is inversely proportional to the square of the distance, inversely proportional to the square of the distance. Inside the earth, it is directly proportional to the distance. So these relations are shown graphically. In the graph, on x-axis we plot the distance from the center of the earth, on y-axis we plot acceleration due to gravity. Then we will get the curve as shown in the figure. Initially we get a straight line. This indicates that the acceleration due to gravity increases with the distance from the center of the earth. It shows that the acceleration due to gravity is 0 at the center of the earth, and it increases with the distance from the center of the earth until we reach the radius of the earth, that is the surface of the earth. Thereafter, the acceleration due to gravity falls off rapidly with the distance. It is inversely proportional to the square of the distance. So the curve beyond the top maximum point gives, the curved path gives the variation of acceleration due to gravity with height. This comes from the relation gh is proportional to 1 by r square. Variation of small g, acceleration due to gravity with latitude. Now let us first try to understand the latitude. Imagine the circle as a sphere earth, and O is center of the earth, OX is horizontal, equator, and from this P is a point. P represents a body of mass small m. A circle is there at P, which is a body of mass small m. Its direction from O to P. OP is making an angle phi with OX. This angle is known as latitude. As P moves from X to the top, the angle phi increases from 0 to 90. Like this we have to imagine the latitude angle. Then if the angle made by OP is phi, then we consider two forces here, because the particle P will be rotating in a circle of radius r. It will be rotating about the axis of the earth, with a radius small r. The radius of the earth is taken as capital R, and the radius of the circle in which the particle is rotating is taken as small r. Now, the particle mass m, small m, it experiences a centrifugal force mv square by r and gravitational force mg. mg is towards the center of the earth along PO, and mv square by r is away from the center of the circle, horizontal circle. And the angle between these two forces, mg and mv square by r, is say theta. That angle theta will be equal to 180 minus phi. The angle between PO and centrifugal force mv square by r is theta, which is equal to 180 minus phi. Now we take these values and we consider mg is equal to force P, mv square by r is equal to q, and the resultant of these two is taken once again as capital R. This R is different from radius of the earth. Though I have used the same symbol, this indicates the resultant force. This indicates the resultant of mg and mv square by r. Now I will take the relation which is derived in vectors. R is equal to square root of p square plus q square plus 2pq cos theta, and I will substitute the values. P is equal to mg, q is equal to mv square by r, theta is 180 minus phi, and small r, radius of the circle, is equal to capital R phi, cos phi, capital R cos phi. By using these relations, I will obtain the resultant weight. When the particle is at a latitude phi, it experiences two forces. One is gravitational force mg, the other one is centrifugal force mv square by r. If phi is the latitude, the angle between these two forces is 180 minus phi. Hence, the resultant weight of the body, capital R, is given by the relation square root of p square plus q square plus 2pq cos theta. Here we take p as mg and q as mv square by r. Let us substitute these values. We have the relation r square is equal to p square plus q square plus 2pq cos theta. Hence, r square is equal to mg whole square plus mv square by r whole square plus 2 into mg into mv square by r into cos 180 minus phi. Let us substitute the values of p, q and theta. We will get r square is equal to mg whole square plus mv square by r whole square plus 2 into mg into mv square by r into cos 180 minus phi. Let us simplify this. So r square will be equal to mg whole square plus mr omega square whole square. V square is r square omega square. Hence, mv square by r becomes mr omega square. So, mr omega square whole square. Cos 180 minus phi is minus cos phi. Cos 180 minus phi is minus cos phi. Hence, we will get minus 2mg into mr omega square cos phi. Minus 2mg into mr omega square into cos phi. Therefore, r square is equal to mg whole square plus m into r cos phi omega square whole square. Small r is equal to capital R cos phi. Now let us use this value. So we will get mr omega square whole square becomes equal to m capital R cos phi omega square whole square minus 2mg into m capital R omega square cos square phi. M capital R omega square cos phi into cos phi, cos square phi. Now let us consider mr cos phi omega square whole square and minus 2mg into mr omega square cos square phi compared to mr omega cos phi whole square compared to mr cos phi omega square whole square compared to mr cos phi omega square. Mr cos phi omega square whole square is very small. Mr omega cos phi whole square. Mr cos phi omega square omega is small quantity, omega square is still small, so omega square whole square is still small. Hence, compared to mr cos phi omega square, compared to mr cos phi omega square, mr cos phi omega square whole square is very very small. Mr cos phi omega square whole square is very very small, so we neglect this. By neglecting this, we will be left with two terms, mg whole square minus 2 into mg into mr omega square cos square phi. Let us take out common m square g square. If we take m square g square as common, we will be left with 1 minus of 2r cos square phi omega square by g. 2r cos square phi omega square by g. So, let us find the square root. By writing the square root, we get r is equal to, capital R is equal to mg into 1 minus 2r cos square phi omega square by g whole to the power of half. 1 minus 2r cos square phi omega square by g whole to the power of half. By expansion series, we can write this as, by using the expansion series in mathematics, we can write this as capital R is equal to mg into 1 minus half into, this half is from power, 1 minus half into 2r cos square phi omega square by g. 1 minus half into 2r cos square phi omega square by g. Let us further simplify this. By cancelling 2 in the relation r is equal to mg into 1 minus half into 2r cos square phi omega square by g, in the relation mg into 1 minus half into 2r cos square phi omega square by g, by cancelling 2, we will get r is equal to mg into 1 minus r omega square cos square phi by g. 1 minus r omega square cos square phi by g. If we suppose the acceleration due to gravity at the latitude phi is represented by g phi, if we assume the acceleration due to gravity at the latitude phi as g phi, then r becomes, the resultant force becomes mg phi. This is weight, resultant weight of the body. Actually it is mg. Here g represents acceleration due to gravity at the poles and g phi represents at a latitude phi. So mg phi is equal to mg into 1 minus r omega square cos square phi by g. Mg phi is equal, mg phi is equal to mg into 1 minus r omega square cos square phi by g. By cancelling m, we get g phi is equal to g into 1 minus r omega square cos square phi by g. G phi is equal to g into 1 minus r omega square cos square phi by g. Or g phi is equal to g minus g minus r omega square cos square phi, r omega square cos square phi. This is the relation for acceleration due to gravity at a latitude phi. From this relation, we notice the acceleration due to gravity depends on the latitude phi.